and welcome to Frame for Light. I'm Dave Kelly. This program is designed to help the viewer develop a greater appreciation for both the art and the science of photography. Over the years, I've talked to people about photography, and many times the conversation seems to go toward the person I'm talking to not wanting to talk about science. They want to talk about the art and the creative side of photography and that which is more fun. And that's understandable, and that's to be expected. But when it comes to science, they will say, well, you know, I find science to be rather tedious. It's kind of hard to understand, and I find it to be actually kind of a bit boring. And so I'm hopeful with this show that I can demonstrate that science can actually be something that's understandable and also can be utilized to enhance the creative side as well. So let's go ahead and get started with a discussion about light and how we capture light, which is the basis for photography. So the first image that I've got is a slide called photograph. So what does the word photograph actually mean? Photograph is actually a combination of two Greek root words. The first word photo means light, and the second word graph means to write or to record. The next image shows you how we generate light electrically, because light is electromagnetic energy ultimately. And this image is of the Emmy Award, and this is the perfect metaphor for what we're talking about. This shows the muse of art, the angel, holding up the atom, which represents science. And so there you have that merging of art and science. In that atom that she's holding up, you can see electrons moving around in an orbital shell. And that shell generates a lot of energy. It actually absorbs and emits photons, which is called the quanta energy process, which is where we get quantum physics. We won't go there, but that's the basis of quantum physics. And through that electromagnetic energy, the sun radiates waves. Those waves ultimately end up becoming rays as we see them in photography. Now, rays consist of oscillating frequencies with varying wavelengths. And if you look at that image on the left, we have a series of squiggly lines which actually represent all of the color spectrum that's in the rainbow. Each one of those wavelengths has a different frequency and a different length, but together they're combined. And when they travel together, as they do normally, they're in a synchronous phase traveling in a singular plane. That singular plane can also be known as a straight line. So light travels in a straight line. So unless they're disrupted, these light rays form clear, bright light known as white light. If you've done any painting on a canvas, you know that when you combine all the colors from your palette, you bring all the colors together, you have the color white. That's a combination of all of the other colors. And that's the same process in photography. Instead of having white paint put on a canvas, we just have clear, bright light, combining all of those colors from that electromagnetic energy. Now, how can we prove that light rays actually travel in a straight line? Well, that's very easily proven because of shadowing. In this image by the ocean, you can see that the sun is coming from the upper right-hand part of the screen, and when it hits that rock in the foreground, that rock is blocking the light path, and so you have shadows occurring behind the rock. And so this proves that the light can't travel over the top of the rock or go around either side of the rock. It just gets blocked. But it actually doesn't get blocked. What's happening is the light is being reflected off of the rock, as you see on the front side of the rock. And there's also energy being absorbed in that rock. And so the energy that's absorbed we feel as warmth and heat. So you get both heat and light from electromagnetic energy. And if you look at the rest of that image, you see that everywhere you look, you have light being reflected off of the ground, off of the other rocks, off of the water, and everything looks as normal with reflected light. If we go to the next image, we can see another example of how light is blocked by an object. Those are totem poles, which are, if you look at the back side of the totem poles, they're all dark because the light can't creep around the side of those totem poles. We know also that the sun is low in the sky. This is probably toward evening as a result of that. And we can tell that because the shadows are getting long behind those totem poles. The longer the shadow, the lower the sun is in the sky. So the angle of the sun will have a direct bearing on the length of the shadow. So if we go to the other side of the totem poles and we look at them from the front, you can see the same principle applies here. The light is clearly being reflected off of the front of those totem poles, and the shadows are casting long on the ground. All right, so this is an example of light that's coming again straight down from the sky. The sun is very high in the sky here. We see this man walking under the bridge. And the light is not getting into that area under the bridge because it's blocked. But we also see that the light is very bright in that courtyard behind him. And we know that the light is behind him, or in other words, he is backlit because there's a shadow on the ground in front of him. So that means the direction of the sun has to be behind him. Now, I enjoy looking at photos like this because the backlighting creates what is essentially a semi-silhouette here. It's not a full silhouette because we can still see the front of the man, but we can't see his face and we can't see the expression on his face. And so that semi-silhouette lends to a series of questions that the viewer will ask when they look at this image. What is this man's attitude? What is his disposition that day? We don't know, but that adds to the mystery of photography. So we're using the science to complement the art, the science of backlighting to complement the artistic interpretation of the image in front. So if we go to the next slide, we're going to talk now about deriving color from the various wavelengths in that electromagnetic spectrum. So the wavelengths can be measured actually based on the frequency of oscillation in each one of those waves. There you see the waves lined up one next to the other. We have violet at the top, blue, green, yellow, orange, and red at the bottom. The violet wavelength is the most high frequency because you see the frequency of the oscillation curve. So if you go from one oscillation curve to the point of the start of the next oscillation curve, you can see that it is very high frequency on the violet. Blue is also pretty high frequency, green a little less so. And then when you get to the red, the frequency is far less and the wavelengths are actually much longer. So this has consequences when we measure them, and we measure them with nanometers, which is a unit of measurement we'll discuss in just a moment. But the violet wavelength oscillation cycle measures 400 nanometers. With blue, it's about 450. With green, we're at 500. Orange, it's about 600, although some would say closer to 620. And with red, we're up to the 700 nanometer range. So those wavelengths are measured as nanometers. And a nanometer is a unit of measurement which is equivalent to 1/1,000,000th of a meter. So let's talk about the metric system for a moment. You know that a yardstick, which is not metric, is about 36 inches, or it's exactly 36 inches. If you go to a meter or a meter stick, it would be around 39 inches. So a meter in the metric system is divided in increments of 10. And so if you have a centimeter, it would take 100 centimeters to equal a meter. If you go with millimeter, it takes 1,000 millimeters to equal a meter. And we talk a lot about millimeters in photography, and we'll discuss that more in the next episode. But with a nanometer, it takes 1 billion of these very small units of measurement to equal a meter. So the scale of nanometers is one human hair. The width of it would be about 80,000 nanometers. And with paper, the average width or thickness of one piece of paper is about 100,000 nanometers. So this again gives you an idea of how small the measurement is that we're talking about. If we go back to the listing of the various spectrum, we see that 400 to about 700 nanometers is the visible spectrum of light. Now, electromagnetic energy includes various other spectrum as well. If you go below 400 nanometers, you're now in the region of ultraviolet light. We can't see ultraviolet light, but we know it exists and it's used in various applications. If you go even lower than that, you're getting into X-rays and then gamma rays that are very high frequency increments of energy, and gamma rays, X-rays are used in medical applications, and we know that if you're not careful, those can be damaging. Now, if you go to the other side of the spectrum, when you get past 700 nanometers, you're into infrared light. Infrared light is not something that we can see with our eyes, but it is utilized in certain applications of photography and also with night vision goggles for folks in the military who need to see things at nighttime that cannot be seen with the naked eye. So if you get even more into the spectrum beyond infrared, you then move into microwaves and then into radio waves and broadcasting. So those longer wavelengths are not dangerous like the high frequency waves are at the other end of the scale. So there's a whole range of spectrum in electromagnetic energy, but we're focusing in photography only on the 400 to 700 nanometer range. All right, so another interesting aspect of light that's synchronous and traveling in a single plane is that if a light ray hits a non-parallel surface, it's going to scatter those wavelengths. So light, which is harmonious and traveling in phase, hits that prism and it comes out the other end in the various constituencies of color, if you want to call it that. And so we have light separated into violet, blue, green, yellow, orange, and red. And that is how we take a look at light separated out. And examples of non-parallel lines include the prisms that we're working with in this example, and also water drops. Water drops exist in water vapor, and they're tear-shaped or pear-shaped, and that's in fact why we see rainbows, because when the rain stops, there are still water vapor droplets, very small, very tiny water droplets in the sky, which when the light passes through them, because of the non-parallel planes of that water drop or water drops, we see the color being separated out into the various components. And you have the same effect with bubbles. When you were a kid, I'm sure when you were blowing bubbles, you would look at the bubbles and occasionally notice rainbows on those bubbles. And that's because the membranes on those bubbles were spherical and circular. And so obviously those are not parallel, and hence you had the rainbow effect. Well, why is the sky blue? Which is the age-old question. People have always wondered, well, why is the sky blue as opposed to some other color? Well, the answer to that is because the shorter wavelengths, which are violet and blue, are much more easily scattered by the atmosphere. So when you have violet and blue wavelengths hitting molecules of oxygen and nitrogen, those spectrum are scattered. We don't see the violet because the violet tends to be scattered much higher up in the atmosphere, and the blue, because it's a little bit longer wavelength, can make it down into the lower reaches of the atmosphere, so we see it when we look up in the sky. And also, the retina in the human eye is designed to detect blue much more readily than violet. Now, this does not mean that all of the blue and all of the violet is scattered in the atmosphere. Plenty of it reaches us here on Earth as well, but a lot of it does get scattered in the atmosphere when we look up. Okay, on the other side of the spectrum is the question, why is the sunset always yellow, orange, and red? And it's because those yellow, orange, and red wavelengths are the longest in the spectrum, and they're the ones that are not scattered easily by the atmosphere or other particles that may exist. And also at the end of the day, when the sun is going down, those shorter wavelengths, in addition to being scattered, also don't seem to be able to reach us at the end of day. The red is the longest wavelength, so it has the greatest chance of reaching us at the end of the day. I should also point out that when you look at sunsets, if you have a polluted sky or polluted air, smog as we call it, smog can also actually enhance the quality of the sunset. It seems counterintuitive, but actually it's the particulate matter in smog that scatters some of the yellow wavelength as well as some of the other wavelengths, so that you end up with only the pure orange and pure red, which makes the sunset much more beautiful. The same thing happens when you look at a sunset over the ocean. Oftentimes the salt particles, the microscopic salt particles that might be rising up from the salt water in the ocean, can actually scatter some of those yellow light waves so that we're only looking at orange and red over the ocean. So it makes the ocean sunset also look more beautiful. Now, these scattered wavelengths can also be rephased. In other words, they can be put back together again in their original composition, which is clear light or white light. So Sir Isaac Newton discovered this in the 1600s when he was trying to prove that color from light originates from natural light. And so he did that by using the prism on one side, scattering the light into its different components, and then using another prism on the other side to recombine it. And then the output, of course, was the white, clear light. All right, let's move on and talk about the time of day and how it affects our photography. Well, time of day has a dramatic effect on your photography because of the wavelengths that are available for you to record. And we know that during daylight hours, midday, noon, early afternoon, and so forth, we have lots of light available to us. We can take advantage of the whole spectrum of wavelengths, so we get everything represented in a picture like this. We see the ivy-covered walls are green. We see the bus in the foreground on the lower right is red. It looks appropriately red. You might be able to see some flowers on the lampposts, and the bricks on the buildings all look to be the correct color. And so this is what you get in the middle of the day, is all of the colors available to be recorded in photography. However, if you have the same exact image, same location in the evening, you end up with sunset and what's often referred to as the golden hour, when everything starts to look more gold, orange, and red. All the colors skew toward the longer wavelengths of yellow, orange, and red, and this is very obvious in this particular image. Okay, let's go back to midday in the same location. If you notice here in this shot, the colors are very saturated. Not only are they available to us, but they're also very saturated. If you look on the lower right-hand part of the frame, you see a woman in a red jacket, and it's very red and bright and saturated. Next to her is a man wearing a blue sweater and pale blue jeans. Those blues and reds are very saturated, look very nice. If you look in the foreground, you see that wall that looks slate gray, which looks like the normal color for that kind of a wall. And of course the greens and all the colors of the flowers and everything look normal. But you go across the water at nighttime, and then you can see that that wall in the foreground that originally was gray is now a yellow golden color. And that yellow golden color exists throughout that image. The water is reflecting a lot of gold, and the ivy on the walls doesn't look nearly as green as it does during midday, and so on. All right, this is a sunset shot that we're going to take a look at here for the silhouette effect. You see that the backlighting of the sun is going down behind the trees, and since we don't have much light in the foreground, all the light and all the intensity of the light is behind the trees, so they go into silhouette. If you notice in the middle of the frame, there is, just above the pool, there's a fountain that's being lit. It's backlit, and it looks very nice with light passing through water. And then in the foreground, you see in the pool, in the middle part of the frame, the light is being reflected, yellow light, and then over on the right-hand side, very nice golden-looking water reflected off of that part of the water stream. Now here's a sunset shot looking out over the city, and we see that the light, if you look in the upper right-hand part of the frame, there's orange light being reflected off of some clouds, and in the foreground the trees are in total silhouette. You really can't make out any details in the trees, so we might want to crop this a little tighter so that we can actually get rid of some of that dead space with those trees, and you'll end up with something like that. And we'll talk more about the cropping and the framing and so on process as we go on in the course. Let's go to the next one. This is sunset at nighttime. You can see there that the last light of the day that we're going to see is going to be that gold, orange, and red light from that sunset. And here's the same idea, the sunset, and in this case the trees are much closer to the camera, but they create a nice silhouette effect against that sky. Now here we have a building that's also affected by evening sun. This is at the USC campus. This is the Doheny Library building. And if you look across that building, you'll see shadows from the palm trees and shadows from other objects that are clearly in the foreground on this. And the areas that don't have shadow, you'll notice look very golden or yellow because that light is starting to change to more of a golden hue. As we go to the next slide, we see the USC Film School. This is the light coming down from the right-hand part of the frame behind that building, but it's reflecting against that sandstone colored wall in the middle of the frame, and I think that's a really nice reflection of that sandstone. It looks really nice. It has a kind of a soft lighting effect. Here's the courtyard at the USC Film School, and there's a statue of Douglas Fairbanks Jr. there. But right behind him, you see three areas where light can be seen in the background, and you'll notice that those sandstone-colored walls are reflecting some nice light in the background. It's a nice little accent for that photograph. And the lighting is very soft otherwise because of the time of day. So we know that evening gives us softer looks in terms of the lighting as the sun starts to go down. I think this is interesting. In the middle of the frame here, I've identified a woman who's on a cell phone who's walking, and she's blurry, and we refer to that as motion blur. And we'll talk about motion blur more in future episodes, but basically she's moving faster than the shutter can capture her in one frame. All right, well, let's go to the next image. This is the USC campus. Again, in the evening, the sun is going down. You'll notice on the upper left-hand side of the frame, the light is washing out that upper part of the image, and it's making it a very soft look. But down on the ground where you see the hedges and the flowers and everything, it looks very nice because it's low contrast, but the color really comes out strongly in this case. This is an example of morning sun, and the morning sun offering a halo effect behind a building. There's just enough light creeping up over the top of that building to provide us with illumination on the foreground of that building, so it's not in silhouette, but it has a nice soft look because of that halo in the morning. Okay, here's another example of how you can utilize backlighting to its greatest advantage, and that is when you have light passing through flags from behind, it really brings out the color and really makes those flags snap, sort of literally and figuratively. And as a result of that, we have a lot of color that we're looking at in those flags, again from backlighting. And this is the shot of a cemetery, which you can clearly see where the sun is in the upper right-hand part of the frame. It's casting some long shadows in that graveyard. And so if you're looking for sort of special effects or interesting effects that are appropriate for a location, this is the kind of thing you want to look for. You want to look for that long shadowing late afternoon sun in a graveyard, which just sort of adds a certain ambience to the image. All right, now we need to talk about the use of artificial light here for a moment, because natural light, which is the sun, is terrific, and we've been talking about that a lot in the slides leading up to this. But sometimes you don't have the advantage of all of the sun, or you're in a place where there are a lot of shadows, or the light is blocked for some reason. And so you have to add supplemental light or flash. And flash is good because it allows us to take photos in places where otherwise we wouldn't have enough light. But there are certain effects that flash creates which are not always as beneficial as we would like. So let's take a look at some of those effects. Well, first of all, with flash, you're getting brightness. And that's obvious because otherwise you wouldn't need the flash. So you need additional brightness. But along with that brightness, you're also going to obtain more contrast in the photograph. In other words, you're going to create more shadows or more high contrast situations between light and dark. And the reason you have so much more contrast is because of the intensity of the light. The light from a flash is very bright, and it sends out a blast in basically a circular pattern. And so whatever is in the path of that circular blast is going to be very brightly lit, and there will be a lot of intensity there. And that intensity can affect the color and the quality of the color that you're getting from that flash. So let's take a look at some examples of the use of flash. In this case, we have an image that is in sunlight, but because of the shack that they're residing in, you can't really see very much. You need more detail, so you have to add what's known as fill flash. So we add the fill flash, and there you can see we've illuminated the whole scene, which is very important. Now we can clearly see the elves. That elf that you see on the back right side of the frame, we couldn't see him at all in the earlier shot. We could see a little bit of the elf on the left, but now we've illuminated the entire scene. You can see where that flash is sort of blasting right into the center of the frame, and if you look above the saw on the saw log there, you see that manual that's got a big reflection off the front of it. And also you can sort of see the perimeter of the light around the edges where the light tends to trail off from that flash. Okay, now here's an example of soft lighting in the evening on a flower, and this is natural light, and this is in the evening time when you want to see a really soft looking effect. The flower is pink and white, and everything around it is in soft focus, so it has a nice soft looking appearance. But if you're concerned that you don't have enough light to capture this image, you might be convinced that what you need to do is add flash. But look what happens to the color of this flower when we add flash. It changes everything. It creates a lot more contrast. It's a much harsher look. Also, those perimeter areas have gone dark, most of them. We still see the flowers around the edges, but a lot of that nice, soft background is gone. So we have high contrast, we have a color shift, things just don't look as good as they did before. Okay, here's an example of where you need flash to illuminate the pterodactyl in front of the moon. We needed to make that pterodactyl stand out, so we added fill flash for that. If you look at the aquarium shot, we've got fish who are behind glass, and that's another thing you need to be aware of with flash. Make sure you're not reflecting off the glass or the light or off mirrors and off windows. So you just need to move a little bit, and in that case you can take a photograph of the fish through glass as long as the angle of the flash is not hitting the glass directly. And that's it for today's lecture. I hope you've learned a lot about how light behaves and how you can manage the light and the time of day and backlighting to enhance your photography. Next time we'll talk about optics and lenses and how we can utilize optics and lenses to enhance our photography. Until then, I'm Dave Kelly. I'll catch you next time.